Let's jump right into this explainer and demystify that incredibly complex device you're probably using right now. As you're going to see, all of this modern magic really just comes down to tracking a single 200-year-old idea that kept shrinking and shrinking and shrinking. Think about it for a second. How old is the actual idea behind your smartphone? I want to challenge your perception right out of the gate here. If you think the foundation of modern tech started in some sleek laboratory with silicon and microscopic lasers, you're off by a couple of centuries. For thousands of years, calculation basically just meant using your hands, your memory, or a simple tool like an abacus. But the true blueprint for the computer you use today didn't start with electricity at all. It started with a deeply frustrated mathematician, a mountain of human errors, and a bunch of very precise metal gears.
Section 1. The Mechanical Dream.
Our journey kicks off in the early 1800s with an English mathematician named Charles Babbage. The guy was just completely tired of finding human errors in hand-calculated mathematical tables, so he dreamed up these mechanical calculators to remove our flawed human brains from the equation entirely. But here's the wild part. He didn't stop there. By borrowing the idea of punched cards from mechanical looms, Babbage accidentally mapped out the exact architecture of every modern computer. He envisioned a section to store numbers, a section to process them, and a way to input instructions. Memory, processor, and input. Without even realizing it, he laid out the literal blueprint of the device sitting in your pocket right now. And that brings us to an absolute visionary, Ada Lovelace. Working alongside Babbage, she wrote what is widely considered the very first computer program. But more importantly, she realized these machines were fundamentally about pure logic. She predicted they could eventually go way beyond numbers, composing music or manipulating symbols. I mean, that was pure fantasy for the 19th century. But here's the tragic irony of the whole Victorian era. We have this amazing vision. The entire blueprint for modern computing is sketched out, but the physical tools to actually build it, they just didn't exist yet. Victorian manufacturing simply wasn't precise enough to build Babbage's metal designs at full scale. So progress hit a massive wall, meaning the incredible dream of a programmable computer had to just sit dormant, waiting nearly a century for reality and manufacturing to finally catch up. Section 2. Logic and vacuum tubes. Progress kind of crawled along at a snail's pace until the life or death crisis of World War II. It was the desperate need to break enemy codes that basically forced engineers to physically build the machines Babbage had only dreamed about. The brilliant British mathematician Alan Turing helped design machines to crack these codes, but in doing so, he laid the ultimate theoretical foundation for computing. With his Turing machine concept, he proved a computer is really just an engine for pure logic. Basically, any problem in the world, if you break it into clear, logical steps, can be solved by a machine. Well, to make Turing's logic a reality, engineers in the United States completed the ENIAC computer in 1945. 17,000. That is the number of fragile, boiling hot vacuum tubes it required just to operate this single machine. I mean, it filled an entire room, generated enough heat to bake a cake, and sucked down absolutely massive amounts of electricity. Now, you might be wondering, why on earth did it need 17,000 vacuum tubes? Because every single one of those massive glass tubes was simply acting as a tiny switch. It was either blocking electricity or letting it flow through. Off or on. 0 or 1. This right here is the birth of the binary system. And guess what? Every single computer today still uses this exact same system to store and process information. The switches haven't changed their basic function at all. They've just evolved. Of course, running a room full of incredibly hot glass tubes was, well, deeply impractical. Programming back then wasn't sitting comfortably at a desk typing on a keyboard. It was an exhausting, highly physical act of hauling thick cables around and manually flipping mechanical switches for hours on end, just to change what the machine was doing. If we were ever going to use computers for anything beyond military calculations, the hardware desperately needed an upgrade. Section 3. The Great Silicon Shrink. All right, this is the true climax of our story. In 1947, scientists at Bell Labs invent the transistor. This tiny, solid-state device does the exact same job as the fragile vacuum tube, acting as a simple electrical switch, but it does it vastly faster, way cooler, and using a tiny fraction of the power. It completely set the world on a path to getting dramatically smaller. And it is amazing to watch how fast this snowballs. From a single transistor in 1947, engineers quickly figured out how to etch whole circuits directly onto a tiny chip of silicon by the late 1950s. Fast forward to the early 1970s, they actually crammed an entire computer's central processing unit onto just one tiny chip, the microprocessor. Engineers quickly noticed an incredible pattern taking shape here. As these silicon switches got smaller, they could pack more of them onto a single chip. Computing power just absolutely skyrockets. By the 1980s, roughly doubling every couple of years. The brains of the machine were suddenly pulling off billions of operations a second on a sliver of material literally smaller than your fingernail. Because these microprocessors were getting so incredibly tiny and so affordable, a monumental shift happened. The switch finally moved out of those top-secret government research labs and directly into your living room. Companies like Apple and later IBM could finally afford to put millions of these microscopic switches into personal computers. Babbage's gears had turned into switches, the switches turned into chips, and those chips brought incredible logic into everyday homes for the very first time.
Section 4. The modern binary brain.
So, what does this whole 200-year journey mean for you, right this very second? Let's break it down. When you tap an app, it triggers a very specific sequence. First, your physical tap is translated into binary code. Second, your microscopic processor reads those ones and zeros step by step. Third, it grabs data from memory to perform tiny logical operations. And finally, the screen visually responds. Because this happens essentially instantly, it feels like pure magic, doesn't it? But keep our journey in mind. Under the glowing glass of your phone, it's really just billions of microscopic transistors flipping electricity on and off incredibly fast. It's Alan Turing's logic, executed on Bell Labs' transistors using Charles Babbage's architecture of memory and processing. It's just happening billions of times every single second. When you really strip it down, from Babbage's clanking metal gears to the glowing, heat-radiating vacuum tubes of ENIAC, all the way to the completely invisible silicon chips we rely on today, the entire story of computing is just the story of one incredible idea shrinking again and again. The idea that any problem in the world, if you just break it into small enough logical steps, can be solved by a machine that only ever answers one basic question: yes or no, on or off, 1 or 0. That grand, crazy dream of a frustrated 19th century mathematician, it is literally alive in your pocket right now, running silently and flawlessly. But seeing how far we've come, from entire rooms of hot glass tubes to invisible switches on a tiny flake of silicon, leaves us with one really exciting question to wrap up on. If a 200-year-old idea about metal gears is powering everything in our digital world today, what exactly will this same relentless, shrinking switch look like in another 200 years? I'll let you chew on that one. Thanks for exploring this amazing journey with me.